You're about to get learned, I guess. All right, so looking at this, we are going to generalize these. So we're just going to say generalize graphs, or graph, either one would work, of f of x equals ... And we're going to have a couple different situations here. Now, as we go through, I'm not going to write down near as much as there is in your, like, that we could. We'll talk about all of it, but we may not write all of it down. If there's a part of it that I mentioned that you would like me to write down, please don't hesitate to tell me. Okay, so when we are generalizing these graphs, I'm going to use this asterisk so it doesn't look like a negative. We're going to graph exponentials. And now there's really two situations that we're going to deal with for these. The first of these, if we have f of x equals a to the power of x with a greater than 1. Now, this could be any number of values, right? Give me some examples of a that we could pick. 2 would work perfectly. And I think if you look through stuff, we graphed 2 to the x. Okay, could we use a 3 or a 4 or 5? If we look at every graph that we've done so far over the last couple of days, did they all have a value greater than 1? When we look at their graphs, did they all have the same common characteristics then? And that's hard to not see, but I think that if I wanted to sketch in general, and you don't have to write this down, but if I said, hey, here's the most general graph of everything that we've done so far, do you guys agree they all looked like this? Every single one we've done so far, right? Now, if a is greater than 1, like this, then what we see is exactly that graph that we just sketched. I'm going to graph it a little bit more general here, and you guys are going to help me work out the points. Now, on these ones, it's always strange because all we require is that a is greater than 1. No matter what a is, if you want to make a table, we can, but it's super weird to do without the number. No matter what a is, if I plug in 0 for x, a to the 0, what is it always going to give me? So no matter what, I think I'm going to have the point right here, 0, 1. Doesn't matter what a is. Now, we can adjust these and add the h's and k's and all that, but in the most general parent function, no matter what, this is going to be on the graph. Okay, what other values would we typically pick for x? Now that we don't have to do any fancy work here. I would always want this to be a 0 because a to the 0 is always 1. What other numbers do we want the exponent to be? 1 is one of them. Now, again, the scale is weird. If I say here's 1, do you believe it? And if I plug in 1, what value does it spit out at me? A. Now, assuming that a is bigger than 1, I don't know exactly where it is, but it's bigger than 1. Maybe it's up here. This is the ordered pair 1, a. And it's super strange to do with just that a value. Dolan answered that one, so I'm not going to give Dolan more candy. But I got M&M, Milky Way, and Twix riding on some answers here. I need one more point on my graph. And they're all weird, right? Because that a value. But anybody have another value of x that we might want to pick? 2 would work. It'd be 2, a squared. But it's not the one that we went with yesterday. -1. Which one of these bad boys you want? Left or right? Oh, lucky. All right. Yep. Don't leave wrappers around, just for the record. Cool. So if I wanted -1, what is a to the -1 going to be? 1/8? Or I know that sounds like for real, you're going to hear me say that a bunch. I don't know how big a is, but can we agree that 1 over a must be smaller than 1? Because a is bigger than 1. Maybe it's here. And here's my ordered pair, -1, 1 over a, or 1/8. Not 8th. Okay, when we graph these, based on everything that we've seen, does this graph look essentially like every other graph that we've seen? Now, there's a few things that we want to deal with this. First of all, if a is greater than 1, which is this exact situation, we see a function that is growing or decaying from left to right. Growth. So we're going to write a few things underneath. This is what is known as exponential growth. Okay, now, right off the bat, I can use these now. This is exponential growth. I'm fine with that. I'm not going to write this one. What is a domain of this function? So I don't think I have to pick greater than 0 because right here I picked one that was less than 0. You might be thinking of the range. The domain is what plugs in. There's nothing that I can't plug in, right? Nothing breaks. I can take a to whatever power I want and everything's okay. The domain is all real numbers. We may as well just include this. The domain, and I'm just going to use DOM for domain, is the set of all reals. Okay, since Christina mentioned it, what is the range of this function? Good. Now, there's an easy way to do this, and I'm going to write it out range in a couple different ways. We could write it in our set builder, which is what I prefer, y such that y is greater than 0. That is always going to happen. Now, alternatively, if we just say all real numbers greater than 0, do you agree that that just means the positive numbers? Like 0 doesn't count as a positive, but it's greater than 0, so that's okay. There is a convenient shorthand here. If you want to use this, and it's just the positives, let's just say it's the reals with a superscript, which is just the up top part. It's not really an exponent because there's no number. A superscript plus. This literally means the positive real numbers. Okay, if you want to use this, cool. If you don't, cool. You do you. Okay, this thing, increasing or decreasing? Increasing. I don't think we need to say that again because we have the term growth written here. Only 2 more things that we're going to ask about with this particular function. Does it have any asymptotes? Is it ever, like, I can go as far as I want to the right. Nothing ever happens. It gets steeper and steeper. There's a horizontal asymptote. Where is the horizontal asymptote? It's at 0 for this one. Will it be at 0 for every function? No. If we move it up or down, certainly that'll change. But for now, there is a horizontal asymptote at y equals 0. And the last little thing. Yes, miss? Because you were here yesterday, right? Okay, so I'm just going to use the same idea. If we look at a real one, and it's going to be easier with that concrete number, what's your favorite value of a base? So if we pick 2 to the x, and I said, let's find f of negative this. Like, it's gross, right? But let's just see what this is. This would be 2 to the negative 100,000. And do you agree that this is 1 over 2 to the 100,000 then? Okay. This is a gigantic number. And it's like, I don't know what it is, a trillion, probably in that range. If you have 1 out of a trillion pieces, do you still have something or do you have 0? It's really close to 0, right? Is this, if I do it further, is this even closer to 0? But does it ever quite get to 0? And if we approach a value and get as close as we want but never quite touch it, we call it an asymptote. Yep, like we just logic that one through. Great question. Okay, last one. Is this function injective? What does injective mean? I'm going to ask the question differently. I appreciate that you guys are looking. Is it 1-to-1? Is the other language? How do we check? So you're thinking even and odd is what you're thinking of there, I assume. I'm going to reword the question. Does this thing have an inverse function? There wasn't a whole lot of confidence there. What do you guys think? Is there an inverse function? And maybe there's a way that, and I'm not going to make you guys dig through your notes, but there's a particular question on one of the tests. It must have been chapter 1. What am I doing here? Does this function pass the horizontal line test? Which means its inverse, and I see you trying to do this flippy thing, its inverse would pass the vertical line test because when we reflect it. The fact that this is 1-to-1, all it says is for every y value, how many x's give that y value? 1. That's my 1-to-1 or injective. This thing is injective or 1-to-1. I'm just going to use the word 1-to-1 so it doesn't get too crazy. Now I'm going to write 1, 2, 1. I like the TIE Fighter though. 1, 2, 1. And this implies something really important. Its inverse exists. Now, you may have little bits and pieces of this in your memory. Anybody remember the inverse of an exponential? Okay, I'm fine with that. Somebody, Casey, might have been about to say something. Fair. What's the inverse of a square? So a square root. What's the inverse of a cube? A cube root. And all right, Ms. Holloway, we're going to put you on the spot. What is the inverse of an exponential function? Oh my gosh, there's a reason I love this woman. Logs. Fantastic. All right, thank you, Ms. Holloway. All right, so as we look at it, I think that made her feel really awkward. Cool. All right, we do have an inverse, and as Ms. Holloway just said, it is the log function. Like, these interact between one another. If you're okay with exponentials, you will be okay with logs, as long as if there's questions you ask about them. Sweet. So we have these. There's only one or two little things that we could change. Now, there's a lot of variations that we could make. I want us to consider this other one. I'm going to switch to this orange color. We're going to consider one more function. I want f of x equals a to the negative x with a greater than 1. Now, we didn't do a single graph like this. I think we should build one. You don't have to physically sketch this out because making the table and stuff is essentially the exact same. But I'm going to sketch one out with your guys' help, and we'll make sense of it. And you know what? Maybe we could just do it with a. Yeah, let's just do this with a. So I'm going to draw a graph again, and you guys can graph this one because we'll just do it with a. What do I want to make this exponent still? You're probably going to be right if you say 3 numbers. 0, 1, and negative 1. So let's try those. If I plug in a 0, what's a to the 0? Or a to the negative 0 if you'd rather? It's still 1. Like, it's the exact same number. So even if we're here at a to the negative x, we get this point, 0, 1. No matter what a is, because it's to the 0. Okay, give me another value of x that we might pick. Negative 1. Okay, I'm going to do some scratch work. If we try to do a to the negative 1, because that's what we just plugged in, right? This becomes a to the 1. So if I go to negative 1, I'm just going to have negative 1 and a, which if a is bigger than 1, it's somewhere up here. Negative 1 and a. Now, I'm building the table, quote unquote, just as I'm doing it. If I'm losing you in this process, I can build a physical table. It's just weird to do with the number a because there's no real number. Questions here? Okay, give me one more value that we might pick. Negative 1, 0, and 1. Cool. So here's 1. If we do the scratch work over here, we get a to that negative 1, which is what? 1 over a, which probably somewhere down here, right? Now, in this graph, do we get the same general shape? For sure, it's that same sort of curve, but there's a fundamental difference about these. Somebody said it louder. This is exponential, no longer growth. And remember, shorthand for exponential, EXP, this is exponential decay. Now, I don't know that I'm going to do as much with this one. What's the domain of this lovely graph that we have on the board? All real numbers. If they're all the same, I'm not going to write this stuff again, okay? Okay. What's the range of this lovely exponential decay function? All positives. Again, like, same thing. Is there an asymptote on this graph? Yeah, and it turns out it's the exact same asymptote. It's y equals 0. Is this function 1-to-1? Yeah, I can pass the horizontal line test, which tells me that this function has a what? It is injective. That's just another word for 1-to-1, but it means something exists. its inverse function will exist. Everything is the same, except now instead of growth, we see decay. Is there another way that we could get the graph of decay, do you think? Okay, so I bet there is. I'm going to pop over to Desmos, if you guys are cool with it. I see you guys writing, but I can't tell if you're writing the same stuff here. That's not going to take me to Desmos. So let's just play around with it and see what shakes out. Desmos. All right. We're going to pick some values here. We've already done 2 to the power of x, and we see that it's growth. Okay, if I do 2 to the negative x, it should be growth or decay? And we'll do negative x. It is. Fantastic. Whether it's 2 or 3 doesn't matter. Every value of a that we've chosen so far has been what? We made a comment on ours when we're doing these graphs. What? Greater than 1. Is there a natural thing that maybe we could try just while we're looking at Desmos? Instead of greater than 1, give me the alternative. Less than 1. Now, we require greater than 0, otherwise wonky stuff happens. Give me a number between 0 and 1. 1/2 is a good choice. When I raise this to the power of x, what are we going to see? It's 2 options. It's either growth or decay. On the count of 3, just shout out what your gut says. 1, 2, 3. Okay, that was not great. That's right. It's decay all of a sudden when we move to a value less than 1. Now, what if I make this a negative x? Now it turns back to growth, and we get this wonky thing happening. I don't want to have to do all 4 of them, which is why we generalize a to the x is growth, a to the negative x is decay, if a is greater than 1. If you wanted to add the other 2, where a is between 0 and 1, you can, and it works out. Just to give one last little thing while we're here, we always require greater than 0. Because if I do this, there it is, we can't even see it. It's not continuous. We just get a bunch of points that don't connect together because it just goes back and forth. We have a bunch of imaginary stuff showing up. This will never happen. Cool. All right. So we're going to do some mathy problems. Okay. This one-to-one property is incredibly important, and we're going to make use of it right now. Cool. Questions about any part of the graph before we go? Okay. So, go ahead. She wouldn't commit to raising her hand. Okay. The fact that one-to-one is easily like the most important thing that we get out of this. Now, we have to be able to do with the graphs. You may look at this and recognize these shapes from COVID times. Kind of a bummer that we had to learn so much with exponentials due to, epidemic or pandemic. What was it? Pandemic. Yeah. All right. Anyway, we are going to sneak in and help me out here. What bullet point are we working under right now? Do we have a bullet? Exponential functions? Yep. Okay. So we are still talking about exponential functions. We're going to talk about exponential functions the whole time, but let's talk about solving exponential equations. So solving equations. And I'm going to say solving exponential equations, but I'm going to use my EXP as the shorthand for exponential. Okay. Now, I'm going to leave a little gap here, and we'll define it here in a second, but this is like our guiding light. And we're going to see if you guys can help me make sense of what this is once we do a problem. Okay. We have this property called the one-to-one property. Now, we see the one-to-one property show up in a lot of different places. With logs is the first time that it shows up in, I would argue, sorry, not logs, exponentials, that it shows up in a super meaningful way. This is a one-line thing that we're going to write here in just a second. We'll come back to this, but we're going to solve a few problems first. We're going to try. So I'm going to throw you guys a couple problems just to see if we can come up with them. We'll start super easy, and we'll do an example, and we'll just say solve. And we're going to try to make sense of these. Now, if we have to come back and do this because nobody can do it, we'll deal with it. But let's check. I want us to solve the following. I want to know, when is it true that 2 to the power of 2x minus 1, when does this equal 4? All right, I'm going to put 3 problems here. B, I want to know when is it true that 2 to the x equals 32? That one might be the easiest. And on C, I want to know when is it the case that 1/3 to the negative x equals 27. I'm going to give you guys 1 to 3 minutes without defining this property to see, bless you, what you guys come up with. Bless you twice. No third time. Okay, cool. Talk it out, see what collectively we remember about solving these, and we'll come back and see if there's gaps. How do we clean them up? Cool, do it to it. All right, so as we look at this, I heard a lot of the same stuff. Real quickly, it's not good or bad. Thumbs up says, yep, I can do these. I remember exactly how to do them. Thumbs down says, nope, anywhere in between. Okay, we're going to make this really easy. And I think that once we write the property, it'll be obvious, but I want to try it here. I'm going to start at B, and that's a random one. This one works really nicely. Does anybody know what power of 2 is 32? I think it's the 5th power. Now, here's, if we're doing this, I wouldn't just write x equals 5. I'm going to look at this. This problem is hard to think about right now, but Dolan, you had a specific language that you used, and I heard you say it. How would I rewrite 32? If I write it like this, do our bases match? Now it's 2 and 2. The second these match, it looks like magic. There's a better reason for what's going on. It's actually called the one-to-one property. If they match, I'm essentially just going to think they undo each other. Now, there's better stuff going on here, and we'll see it later in the chapter. But if these exponents were held up by these guys, if I cross them out, do we all agree that it just falls down and it lands here? Like, if I think of it as a physical structure that holds up my exponent and they're gone, everything else just falls, and we get x equals 5. This works really well if we have the same base. Like, that is the important part. We're going to refine that idea really quickly here, and we'll come back and work on. We're going to say that for exponentials, and we're going to see the same thing with logs, and it happens with a lot of different stuff, but here's our one-to-one property. For a value, and we're just going to say for a greater than 1. For any number a greater than 1, we're just going to make the following. A to the x is equal to a to the y if and only if what must have been true. We just used it. So they do have the same base. They match. Good. X equals y. If I say, hey, I'm thinking of 2 to the 7, and I guarantee that's the same as 2 to the what number? Could you guarantee it's the same as? That was hard because you guys were probably thinking. If I say, hey, I'm thinking of the number 2 to the 7. Okay, I want you to think of a number that's the same, and it's going to be base 2. 2 to the what is the same as my number? 2 plus 5. So that's harder than I was thinking. Do we all agree that we could just say 2 to the 7 is the same? Yeah, that's what's going on here. Like, that's it. If our bases match, and we're going to make this more general. If bases match, which these are my bases, match, simply set exponents equal. That's it. Now, sometimes this is easy to do in each of these problems. It's not terrible to do, but you do get a little bit of freedom in which way that you choose. So when we're looking at these, nobody probably, until I wrote it, did it this way. You probably just thought it out and said it's 5. Okay, this is the work that goes into it when we get uglier problems. So if we look at A right now, do the bases match? Not yet. Now there's 2 ways that we can do it. I can either try to write this number 2 with a base of 4. That's an option. Or I could try to write the number 4 with a base of 2, as long as they match. I think that's the easier way. So let's not touch this side since it's already a base of 2. And I think it's still just 2 to the power of 2x minus 1. How on earth can I write 4 with a base of 2, though? 2 to the 2. As soon as we get to here and my bases match, my very next line, whether you actually draw that cross out or not, I'm simply left to solve when is it true that 2x minus 1 equals what number? 2. And I think we can all solve this. What do you guys get for x? I think it's 3/2, because we'll add 1 to each side. We'll have 2x equals 3, and then we'll divide by 2. Now, could we check on our calculators to verify? Like, you could probably do 2 to the 2 times 3/2 minus 1, and you could check it. I guarantee it's 4. If we wanted to make this instead of a base of 4, we could. Do you guys recall properties well enough to do that? Okay, we'll review our exponent properties here in just a second. This one, a little bit harder, and immediately those exponent properties that I was just alluding to show up. Well, there's some options. We could make this 1/3 with a base of 27, which seems like a weird thing to do. But we could also make this 27 with a base of 1/3, which also kind of seems like a weird thing to do. Ugh. Thoughts? Is 1/3 a power of a number that you know? I think so. I'm going to have a challenge for you. I'm going to give you a big push. There it is. It's 3 to the power of -1. Now, I recognize in this one, because we don't have an easy way to connect them, and we could do it as base 27 or base 1/3, gross. Can we all agree that this is the same as 1/3? And we'll review, like, we'll have these properties. 3 to the -1 is 1/3. That's just how our rule works. And it's still to what power? To the negative x equals, now, is there a way that we can make 27 have a base of 3? 3 times 3 is 9 times 3. Hey, it's 3 cubed. Okay, at this point, we're close. We have both of these expressions written with which base? 3. The only property that we haven't quite addressed yet is I have 3 to the power of -1 to the power of -x. And we haven't reviewed all of these. What on earth happens? We straight up just times or multiply them. 100%. So this is going to be rewritten. 3 to the -1 times -x is 3 to the x equals 3 to the power of 3. And now, what's x? 3. Now, it is not the only way to do this problem. There's a bunch of different ways. I'm always going to look for what I would consider, and I hope that what you guys agree is the easiest way to go through it. Yes, Can you explain again? From here to here? Yep, and I'm gonna, let's get some properties here real quick, and then if that doesn't clear it up, we'll come back to it. Okay, so for these, we are going to use a variety of properties in doing these, and we haven't seen all of them. I think you've probably seen all of them at least at one point, but I'm just gonna put in here, let's see, we just need a tilde. Here we go. Some exponential properties, and really some exponent properties. Okay. Here is the deal. I'm not a huge fan of just memorizing stuff, not just by brute force, which just means like sitting down and trying to memorize it just right then and there. I like the idea of memorizing stuff by doing, because if you just do it so many times, eventually it just gets ingrained. You don't have to think about it anymore. Do you guys know any powers of numbers pretty easily? Like, do you guys know powers of 2? Okay, so here's what I want to think about. I'm going to do a bunch of scratch work over here. And for these, we're going to try to work out some props. I'm going to use 2 and 3 as my numbers. If I wanted to take 2 to the 2 times 2 to the 3, could we do this? Now, you may not remember the exact rule right now, but we're going to work it out. We'll do it 2 different ways. Here, we'll see if there's an exponent way to do it. And then down this way, we'll just do it like expanding everything. What's 2 squared? Times, what's 2 cubed? So that gives me 32. Do you guys agree? Is 32 a power of 2? Which power based on B here? 2 to the 5. So without remembering the rule itself, What we've just worked out, and we're going to generalize it here, is one of our rules. This is the product or multiplication rule for this. If I have a to the power of x times the same base, a to the power of y, how on earth could we use this single example to get my generalized rule? Weisha's confidently whispering it. If everybody can hear her, you probably heard it. How do we get 2 and 3 to get to 5? We add them. Awesome. A to the x plus y. Now, this is a property that we're going to use all the time. If you want to just commit it to memory, I'm cool with that. But being able to work it out on your own is so much more valuable because then you don't have to just strictly remember stuff. Now, one could argue you have to remember how to work it out, but just a concrete example of the property that you're trying to figure out is, I think, easier in my head to remember. Okay, let's get another one. What if I took, and I'm just going to keep those numbers, 2 squared divided by 2 cubed this time? That's 4 over 8, which is 1/2. And that's the same as 2 to the power of -1, right? Did they just subtract 2 minus 3? Hey, they did, which means we get another property. And I'm going to put an asterisk next to each one. If we have a to the x divided by a to the y, they just simply subtract a to the power of x minus y. Always the concrete examples. So let's see, we took the product of exponentials, we took the quotient. Example C here was not a product or a quotient. Instead, it was like a power of a power, right? So let's try the same thing. Let's do 2 squared cubed. And you may remember the rule. And if you do, awesome. If you don't, awesome, because we can figure it out real quick. This is 4 cubed, right? And what is 4 cubed? 64. Is 64 a power of 2? That's the same thing as 2 to the power of 6. Based on these numbers, how on earth could I get it to become, excuse me, multiply? Yeah. What's my general rule here then? A to the power of x to the y equals a to the xy. Now, Basil, your question. This is the super long answer because I added more stuff. But can you tell that we just did a to the something something, or a to the power, and we just multiplied -1 and -x? Boom, awesome. Cool. There are some other properties. We wrote down one of them yesterday. What's a negative exponent do? Good. It's just 1 over a to that power, now positive. Okay, deal. Huh, cool. We are at a point where maybe we could do some homework already. Gosh. Do you guys recognize the name Leonard Euler? E-U-L-E-R. It looks like Euler. E-U-L-E-R. So like an Euler's disk. Yep. Okay. I'm going to write a number on the board. We may not continue with this today. You don't have to write it right now. Okay. All I want you to do is tell me this number. Ooh, have we seen the number E as students in here? It's not base 10. Okay, so very different. This is what your calculator does. Capital E is different. Have you guys ever seen this number? Yes. I don't know what it is. I can't get a read on you guys. Have you seen this number? Yes. Okay, what's it? And approximately what? 2.14159. 627 is all I know. I don't remember. Okay. Well, here, this is the number E. It is. Okay, so that one didn't go as well. My guess is you guys have seen it very little. I have a stupid joke that's a really good way to remember some stuff coming up. Tomorrow, we are going to start looking at the number E and some applications of this stuff. You guys, I guarantee, have dealt with interest.
Yes.
Like, not like obviously everything that we talk about is interesting, but you've talked about interest. Like, if I put money into a bank and it gets this % return every year, this number would have showed up there. It is approximately 2.7828, blah, 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 blah. Okay. I can't, so you did find out on the calculator. Am I right? 71828? And it keeps going. It's just like pi. Yep, I don't remember any, half the time I don't remember 2.71. Okay, here's the deal. We're going to look at those, and we're going to see that number tomorrow. If we've never seen it, now is not the right time to start talking about it. So we got to adjust your homework then. Let's figure out what we're going to do. You get a little practice with some exponential stuff. All right. Oh, man, this section is so cool. This whole chapter is really cool. You guys are lucky. All right. Now, there's little bits and pieces that we have not spoke about, right? Like naturally. I just want to remind you, it is always going to happen. There's things that we've talked about this year that we haven't talked about recently that could possibly show up on the assignment. If it happens, as long as you come and talk to me and ask, I'm cool with it. Like, we'll try it out. For today, or tonight, right now, I guess, we're going to knock out homework 3.1.1, which is waiting for you on page 208. And I want you guys to do 13 through 16. 23 through 26. And 33 by hand. Cool. You'll see why it says use a graphing utility. Don't use your graphing calculator. Just make a table by hand. Like, I promise there's a reason I'm having you do that, not because I'm anti-tech. Okay. This will be due tomorrow. Okay. Sweet. I'll give you guys the rest of the time to start looking at stuff. Cool.